To finish off part D, we now want to graph the function as best as possible. I think the book actually says sketch. We'll do the best we can. Using all the information we have so far, and maybe a little bit more. We need to get a little bit more information. I'm just going to use scale 1. I remember that the relative minimum was happening at 1, e, so I should be able to plot that on here if I use scale 1. 1, e, 1, around 2.7. So maybe somewhere here. Let me just rewrite the function rule I have in front of me. Okay, it's pretty clear that this has a vertical asymptote at 0 because the bottom would become 0 at that location. So I can draw in a vertical asymptote there to help me sketch this graph. So that is x equals 0 there on the y-axis. Okay, so we now know there's a relative minimum happening here. So I can at least sketch in a little structure like this. Right? Every minimum looks like that. And we also know that it was concave up on 0 to infinity. Let me just write out a little bit of the information we know. We knew it was concave up 0 to infinity, concave down negative infinity to 0. We knew it was increasing on 1 infinity, just to get the main points from the work we did above. It was decreasing on 2 intervals, negative infinity to 0 and 0 to 1. All right, this is not enough to be able to draw this graph completely, I think. We may have to do a little bit more work. So we had the relative min, which I've already graphed, because I have to remember the values, relative min at 1, e. So that pretty much describes everything we got from the derivatives. So let's see if we can start filling in a little bit at least. So from 0 to infinity, it's concave up. Already kind of looks like this. It's concave up. But we know it's changing from decreasing to increasing, right? 0 to 1, it's decreasing, okay? So it's probably heading up towards this asymptote there, and it's going down, decreasing in a concave up kind of way. And after the location of 1, it begins to increase also in a concave up kind of way. So those together give us this basic picture here, something like that, for the right-hand side. There's not much more to do on the right-hand side. I think that looks like about it from the information we have, okay? Let's just make sure that this is going up like this towards infinity forever. We could take the limit as x approaches infinity. What happens? What's the end behavior, right? Check on the end behavior. Well, as x goes towards infinity, we have an infinity over infinity case. So it's L'Hopital's rule. Okay? So I can check on this for the right end behavior. Okay. So let's see, L'Hopital's rule would say take the derivative of top and bottom separately and reevaluate the limit. We have the limit as x approaches infinity. E to the x comes back, but x just goes to 1, so I just have this, which is certainly infinity. So I do have my arrow going the right way. It makes perfect sense with what we've drawn so far. I'm pretty convinced the right-hand side is complete. Okay. What about the left-hand side? Let's also check on the left end behavior very quickly. Left end behavior would be the limit as x approaches negative infinity of the same function, e to the x on x. Okay, what happens as you go towards negative infinity? Well, the top, right, the top is heading towards 0. As x goes towards negative infinity on the exponential function, this exponential function gets smaller and smaller towards 0, always staying positive. And the bottom is heading towards negative infinity because that's x itself. So the 0 negative infinity is not indeterminate. It's totally understood this is 0. Okay? So that means we have a horizontal asymptote, only on one side. Right? The function is heading towards 0. That's y equals 0. It's not doing it on this side, only on one side. Okay, very interesting function. It's not like a rational function. So the question is it coming down from here, heading towards this asymptote, or is it coming like this? Which way is it going? Well, let's see. We know it has to be concave down on the left, right? Negative infinity to 0 is concave down. And simultaneously it's decreasing, so negative infinity to 0. So we need to have a picture over here which is decreasing and concave down. Well, certainly this is the only picture, right, that would describe that. Something like that. Okay. Just to be certain, right, we see there's no x-intercepts here, right? There's no way this function ever equals 0. So therefore it's not crossing the x-axis at all. So it's to be decreasing concave down. This is really the only structure it could take on to approach its vertical asymptote. Now you can also check just to make sure, right, what happens as you approach the asymptote from the left. From the right it was pretty clear just from the concave up structure. Concave down structure, it's also pretty clear, but just to solidify this and to use what we've learned before about limits to solidify this even further, right, limit as x approaches 0 from the left of e to the x on x. Well, e to the x is approaching 1, right? It's approaching 1, and it's always positive. But the bottom's approaching 0 and is always negative. So therefore that ratio should be a negative infinity, which is exactly what we see here, right? As x gets closer and closer to 0 from the left, our function picture is approaching negative infinity. It's approaching its vertical asymptote downwards. Okay? So there's the graph of this function using everything we learned from the previous 3 parts of this question.